Hey, this is Zach from ZachMakesGames.com with a quick demo I put together to try and learn quad trees. Quad trees and octrees and KD trees are really useful for any kind of real-time 2D or 3D simulation, especially for things like games, because games are pretty much always a 3D real-time simulation, or 2D if you prefer the side-scroller type things. But they're really great ways to spatially partition data so that we can do easy searches, easy insertions, easy lookups of data and find things like nearby points, nearest point. We can do things like early collision detection based on proximity. There's all kinds of stuff that we can do with quad trees or oct trees that make processing real-time simulations a lot faster. So I put together this quad tree in C# and this fun little demo in C# as well. It's all in C# using Windows Forms. And this is a pretty simple demo of a fire moving through a forest. This is a great use case for a quad tree because it's proximity based. The fire is going to spread to nearby points and not through any kind of random thing, so there's a structured spread for the fire. So right off the bat, you can see that there is a quad tree drawn here. The black lines represent the quads within the quad tree. So we can actually see the subdivision of the space down to its finest granularity. And it's pretty cool to see the points where the quad tree is bigger, where the quads are larger, and where they are smaller too. You can see that they're usually higher density data where the quad tree gets really small. I'm going to go ahead and turn this off though so we can actually see what's going on here. I've got this light green background that would represent the forest floor, and these dark green points would represent trees within the forest. So let's go ahead and pick a random tree and start this simulation. So I've got a tree that's on fire now. It's turned orange, represents it's on fire, and the fire is going to spread within the radius of this blue circle. I can kick this simulation off by manually advancing it one frame at a time by clicking Ignite Neighbors. And what we'll see is pretty much what we expect. The points within the radius catch on fire. Now, this is a little bit of an odd case because these points on the edge caught on fire and this point caught on fire, but these points didn't and that point didn't as well. And this is just a small discrepancy between the granularity of our data. The coordinates of these points have more granularity than the size of the canvas, which makes rendering a little bit funny. The way that this is rendered kind of skews the data a little bit because there's only so many pixels that we have on the screen, and the points have a finer precision to their position. So the math is right. I promise that the math is actually accurate here. I've done lots of testing to make sure. It's just a kind of a poor representation of the data because of the limitations of doing a 2D render to a bitmap. But let's go ahead and keep this going. And pretty much as we expect, the fire will spread out in a kind of a large circle as it grows, and eventually will consume the whole forest. Now I can actually interact with this demo by clicking, and any points that are on fire that fall within the radius of the point that I clicked on will be extinguished. So I can actually modify the simulation on the fly to kind of change maybe how things might work, how things interact. It's an interesting way to kind of tweak the simulation and see what happens. I can also change the spread radius on the fly as well, and that makes some interesting things happen too, where we get these little pockets. So like right here, this pocket of trees isn't catching on fire because it's outside of the radius. And sometimes it does interesting things too, like kind of makes the fire swirl around as it searches for the next thing it can catch on fire. So it makes some interesting patterns, and that's always kind of fun to see. I can rebuild the tree, and if I turn the quad tree overlay back on, I'll rebuild it a couple times, and you can see that the quad tree is shifting, so this is actually real-time generated. It's not just one overlay that I generated. This is rendering the real quad tree that represents the data. And I can also do some interesting things too, like I can run the same simulation without a quad tree in general, and see the timing difference that it takes, because that's the whole benefit of a quad tree, is they're supposed to be faster. So I can actually observe the time change here in the bottom right corner, but more generally, I can actually test the same data set against the different types of search methods with this little time attack application. This is a cool little app because it allows you to generate one data set and do multiple tests with it and compare the time that it takes. So what's going to happen is I'm going to generate 100,000 points, and I'm going to place them in a tree that is 1,000 by 1,000 in dimensions. And there's a little bit of a mistypo here. This should actually be tree half width. I can set the depth of the tree and the search radius and the run count. And what this will do is it will generate 100,000 nodes in the given tree 10 times and search within the radius of a random point, and it'll be the same random point for each of the 3 tests, and then it averages the time that it takes over those 10 runs, so we can see the benefit of a quad tree over the average case in varying data sets. So right here we can see that using a dynamic tree, and this is where the tree is not pre-built, where every time you insert something into the tree, it will subdivide the quad if it has to, is much faster than not using a tree at all. 97 microseconds versus 2 milliseconds, that's a pretty big difference, especially for something like games. But it's interesting to be able to see the difference between using a fixed tree, where the tree is pre-built down to a fixed depth. That means that it's pre-subdivided before anything is added to it. There's actually a pretty big difference in the time it takes. Maybe it's not enough to make a huge difference, but I thought that was really interesting that there's a fairly big discrepancy. And not always, it really depends on the data, but pretty much every time I've run this, the dynamic tree is always faster than the fixed tree, at least at a good depth. So at a depth of 7, maybe at a depth of 4, the timing is a little bit more accurate. But it's a really interesting kind of phenomenon in the difference of data structures, of algorithms. So it's a cool way to show that there are many different ways to do the same thing, and the kind of benefits and drawbacks of each. So this was a really cool project. It was really awesome to actually see the time differences for myself, see it with my own eyes, test it and play with it, and actually understand why we would use something like a quad tree instead of doing the naive method of searching all the points. This was an awesome way to really understand why things are done the way they are in the real world. And I always love doing things that I can see. And if I can work on a project and then visualize it, I learn more from it that way too. It helps me really solidify the concepts of it. So I had a lot of fun with this project. And if you're interested in it, the code is available on GitHub, and I have a little bit more in-depth write-up into what I did with the quad trees and the implementations on my website. So that's linked below. The GitHub is linked below as well. I hope you've enjoyed this little demo, and I'll catch you next time.